Chapter 6. True or false, the basis for all decisions. In Chapter 3, we examined different kinds of operators, namely the arithmetic and relational operators, as well as the logic operators. The arithmetic operators produce a number. The relational and logic operators produce a true-false result. They require a different type of variable for holding this result. It is called the Boolean type. We will use the Boolean type in the decision that we learn to program on the computer. We will also examine the basic control statement, the if statement, which allows us to program decisions on a computer. In this chapter, the Boolean type, developing a model of a decision, program flow, control statements, the if statement, the if-else statement, the switch case statement. The Boolean type. In addition to the types we have already studied in the integer, double, character, and string types, there is another type, the Boolean, named after the mathematician George Boole, who did extensive work in the subject of logic. It is a variable type that holds the result true or false. These values are not the strings true or false. They are the values true or false. The only way to get these values is to use the relational operators, less than, greater than, etc., and or the logic operators, and or not. From Chapter 3. When you compare two numbers with a relational operator, you get a value of true or false. Example: 16 greater than 15, result true. 8.5 less than or equal to 8.2, false. Negative 12 less than 4, true. Now let's declare some Boolean variables and use them in assignment statements with these examples. Because we want to declare more than one Boolean variable at once, we will make a list of variables after the type Boolean. Just separate the variables by commas before ending the declaration statement with the semicolon. Let's use the name flag for one of the Boolean variables, since flag reminds us of the expression to raise a flag and catches our attention. You will later see why this is useful. Variable type, variable, etc. Boolean flag, x, answer, etc. Flag, x, and answer are all Boolean type variables. Example: flag equals 16 greater than 15. Result: flag holds true. Example: x is equal to 8.5, which is less than or greater than to 8.2. Result: x holds false. Answer is equal to negative 12 is less than 4. Answer holds true. Now let's consider some examples where the Boolean type is used with some variables in relational expressions. In the previous example, the values were used directly in the relational expressions. Int a, b, c, semicolon, declaring three integers in a list. Boolean answer, flag, result, double slash, declaring three Booleans. A is equal to 14, B is equal to 0, C is equal to 7. Example, answer is equal to A is less than C. Result, answer holds false because 14 is not less than 7. 14 is less than 7, clearly. Example, flag is equal to B is greater than C. Result, flag holds false because 0 is not greater than 7. 0 is not greater than 7. And then example, result is equal to A is greater than B. Result holds true because 14 is greater than 0. 14 is greater than 0. Tip, when you want to declare more than one variable of the same type, declare the type and then follow with the list of variable names separated by commas. What does a decision involve? It is important that we clarify what... Tip. When you want to declare more than one variable of the same type, declare the type and then follow with the list of variable names separated by commas. What does a decision involve? It is important that we clarify what happens when we make a decision in ordinary life, as we broach the subject of decision making for a computer. We need to develop a model of decision making that is consistent with the way a computer makes a decision. If we practice developing and applying this model in everyday decisions, then we will be better able to adapt our thinking to write the code that allows the computer to make a decision. Developing a model for making a decision. There are many situations in ordinary life where we make a decision, which is a choice from two or more options. Once the decision is made, an option is chosen, then we may have a resulting course of action associated with that choice. Let's review the structure of a decision in everyday life, and later we will apply this structure to programmed decisions. When you make a decision, you must choose one of at least two things. Once the choice has been made, you may be required to follow a specific course of action for that choice. We will call each resulting course of action an outcome. Consider the decision of whether to buy tickets to a concert. The decision is a choice between two options, buying the ticket or not buying the ticket. Decision, option 1, buying ticket, option 2, not buying ticket. Now, what do we mean by an outcome? An outcome is a resulting course of action associated with each option. What is the resulting course of action of choosing option 1? The resulting action could be that you work overtime to make extra money. You get an evening off from work for the night of the concert. You then go to the ticket agency and you spend the money on the tickets. The resulting action of choosing option 2 could be nothing. You don't have to do anything if you decide not to buy tickets to the concert. Outcome 1, work overtime, get a night off, go to ticket agency, buy the ticket. Outcome 2, nothing. Consider another decision from everyday life that involves two options and two outcomes. Your parents are going away for the weekend. They ask you whether you would like to go away with them to the mountains. If you go to the mountains, you can go hiking or sailing on a nearby lake. If you stay at home, you will be all alone, but your mother wants you to paint the porch while they are away. So your decision is whether to hang out with your parents for the weekend or work like a slave while they are away. Let's consider the decision, the options, and the outcomes associated with this situation. Decision. Option 1. Go away with parents. Option 2. Stay home alone. Outcome 1. Outcome 2. Outcome 1. Ride in the car with parents. Outcome 2. Wash porch. Outcome 1. Eat dinner with parents. Outcome 2. Sand porch. Outcome 1. Go hiking. Outcome 2. Paint porch. Outcome 1. Go sailing. Outcome 2. Have friends over if you can stay awake. Depending on which option you choose, an outcome will follow if it exists for that option. The important thing to notice about decisions is what your options are as well as the outcomes for each option. Decisions always involve a choice between at least two options. Once you decide, you then branch off to follow the outcome associated with that decision. See Figure 6.1 and 6.2. Figure 6.1. A decision involves a choice leading to two outcomes, outcome 1 and outcome 2. Outcome 1 leads to the left branch, and outcome 2 leads to the right branch. Figure 6.2. A decision involves a choice leading to only one outcome. The other choice has no resulting action. Let's look at some other examples from everyday life. Put each decision in the context of our model using outcomes. Consider what the decision is in each situation, what your options are, and whether each option has an outcome. Example 1. If you go to the early showing of a movie, you will be home in time to watch a program you like on TV. If you choose the later show, then you should set your TiVo to record the program. See Figure 6.3. Figure 6.3. The choice of the earlier or later show involves two outcomes: watching the program when you return or programming your TiVo now. Back to the text. Example 2. Another decision is how you wish to spend your allowance. If you spend it on a shirt you like, you will not have money for a CD. So you must make a decision. See Figure 6.4. Figure 6.4. The decision about how to spend your allowance shows two options, choosing the shirt or the CD, and two outcomes, purchasing the shirt or purchasing the CD. A decision by its nature always has a choice between at least two things, this or that, yes or no, true or false. A decision must involve at least two options, otherwise it's not a decision. This is true in our ordinary experience, and computer programs simulate that process. Remember, this is a machine, not a thinking being. It has a limited ability to decide. This is a machine that only understands two things, current on or off, which can be associated with integer 1 or integer 0. And now we take this into a higher abstract level of where the integer and now we take this into a higher abstract level where the integers 1 and 0 are used to represent the Boolean values true and false, respectively. Don't worry about how this is done. That's done by low-level programmers. The computer will make a decision based on whether it gets a Boolean value of true or false. For us as programmers, we need to develop Boolean expressions that model our decisions, so we have to make certain adjustments in our intuitive processes to fit this model of a decision with its options and outcomes clearly stated. As you might imagine, the computer has a limited capacity in how it makes decisions. Whether a computer makes a decision, it evaluates a Boolean expression. We use the Boolean type because of its values, true or false. The computer will choose between true and false, and that's it. The computer always chooses true. Through the use of a special programming statement, this computer can be manipulated to execute an outcome. Applying the decision model. Let's examine situations where decisions are made by a computer. In each example, we will look at the decision, the options, and the outcomes. As you read each situation, try to identify the decisions. As you read each situation, try to identify the decision and the outcome. The decision will be framed so that a Boolean expression can be used. Entering a password at an ATM. Initially, this may not seem to involve a decision, but for the computer it involves a lot of decisions. When you enter a password at an ATM, the computer must match your entered password with the information obtained from the magnetic strip on your bank card. The password you type after inserting your card should match the password obtained from the strip. If there is no match, then a message will be printed to the effect of "Your password is incorrect, please enter it again." See Figure 6.5. Figure 6.5. A password is evaluated for accuracy. If the password is correct, access is given. Otherwise, a message is given to try again. Decision. Does the password entered equal the actual password? Outcome 1, grant access. Outcome 2, print message saying try again. Counting the number of people with last names beginning with L. If we want to keep a tally or count of people whose last names begin with the letter L, we need to program the computer to look at the first letter of a name to see if it is the letter L. Each time a name is entered at the computer, we either increase the count of the names or ignore the name because it does not satisfy our condition. So a decision has been made and two outcomes are possible: to count or to ignore. See Figure 6.6. Figure 6.6. The name is entered, after which a decision is made by the computer to see whether the name begins with an L. If it does, the count of names beginning with the letter L is increased. If not, no action is taken. Decision. Does the first letter of the name equal the letter L? Outcome 1. Increase the number that keeps track of the count of last names beginning with L. Outcome 2. Nothing. Heads or tails. Another example of a decision is the one involved in heads you win, tails you lose. If you flip a coin and the head appears, then you have won. The other option is that the tail appears and you have lost. See Figure 6.7. Figure 6.7. The outcomes after flipping a coin are shown, winning or losing. Decision. Does the coin face equal a head? Outcome 1, you win. Outcome 2, you lose. Tip. Decisions always involve a choice between two or more options. Each choice may have an outcome associated with it. Controlling where the compiler goes. It is important to remember that the compiler moves through a program and executes statements in the order in which they are written. If you want to alter that order, and this is important for decision making, you need to understand how to control the compiler. Program flow. Program flow is an important concept. It is based on the idea that the translator of any program we write in a high-level language will sequentially carry out the instructions we write unless programmed otherwise. What does this mean? This means your programming statements are executed in order, one after the other. Look at this example from the programming language BASIC. Notice how the program has line numbers to the left of each statement. This numbering of lines emphasizes the order of translation and of each statement. It helps the programmer to remember that what is on line 10 is executed before what is on line 40. 10. Let x equal 7. 20. Let m equal 2 times x. 30. Print the answer is m. 40. End. Everything is done sequentially unless we direct it otherwise. The translator here is actually an interpreter, translating one line at a time. So in the BASIC program, the interpreter goes from line 10 to line 20, and from line 20 to line 30, and finally to line 40. The compiler, another type of translator, is really similar to a large ball at the top of a hill. Once you give the ball a little push or start to run a program, it will come down the hill and just roll over everything in its way. The compiler is similar in that it won't stop for anything unless it is programmed to do so, because at a lower level it is programmed to go to the next statement. It automatically goes there unless the programmer controls the compiler through a control statement. Control statements. A control statement is in a programming language is a statement that allows the compiler to alter its normal execution of line-by-line execution of code. Certain control statements allow the compiler to skip over one or more lines of code to get another line or lines of code. Some control statements allow the compiler to repeat certain lines of code. The ability to skip a line or block of code is very important when you write a decision, because you want to be able to execute one outcome from all the outcomes that follow the decision. You don't want to execute all the outcomes, but rather you would like the compiler to go to the outcome that it should execute and skip all the others. Our first control statement will allow the compiler to evaluate a Boolean expression and then either go to the next line or skip that line. In order to understand how a control statement works, we need to look at a specific control statement, the if statement. The if statement. The if statement is our first example of a control statement in a programming language. An if statement has two parts: a Boolean condition followed by a conclusion. The Boolean condition. A conditional statement, you might have seen one in a geometry class, is a statement that begins with the word if. A Boolean condition is a conditional statement containing a Boolean expression. Another name for a conditional statement is a hypothesis. In computer programming languages, a hypothesis is formed by using the word if with a Boolean expression. The Boolean expression can be evaluated as true or false. When the Boolean expression within the hypothesis is true, then the conclusion occurs. The conclusion will not happen unless this hypothesis is satisfied, i.e. the Boolean expression is true. So the if statement uses the Boolean expression as a way to deciding whether the conclusion that follows is executed. If the Boolean expression is true, the conclusion is executed. The conclusion. The conclusion, another name for the outcome, is a statement that follows the hypothesis. If the hypothesis is true, then the computer executes the conclusion. The conclusion represents one outcome you would like to have happen when the hypothesis is true. In the examples that follow, each bolded statement is a conclusion. If it rains today, we won't go outside. If I have enough money, I will order tickets. If the password is correct, I will get access to my account and withdraw money. Examples of if statements in everyday circumstances: hypothesis, Boolean condition, conclusion. If it rains tomorrow, we won't go. If you win the game, you advance to the next round. If they get home by 9, we can leave by 10. Let's rephrase each hypothesis with its Boolean expression bolded. In order for any of these conclusions to occur, you need to ask whether that Boolean expression of the hypothesis is true. In the sense, each statement can be rephrased like the following: if it's true that it will rain tomorrow, we won't go. If it's true that you won the game, you advance to the next round. If it's true that they'll get home, by 9, we can leave by 10. Examples of if statements for a computer. Here are some examples of if statements. Remember, the Boolean expression is contained within the part that begins with if. The boldface part is the conclusion. Examples. If amounts of the check is less than the balance, Boolean expression, subtract the amount of the check from the balance. Conclusion. Boolean expression. If password is entered at the keyboard is the same as the true password. Conclusion. Provide access to the account. Boolean expression. If your age is greater than 16. Conclusion. Apply for a driver's license. In each example, the hypothesis can be rewritten using a Boolean expression. Boolean expressions, if you recall, come from using the relational operators less than, greater than, less than or equal to, greater than or equal to, and not equal to. So let's take each of these conditions and rewrite them using relational operators to create a Boolean expression. In each example, we will declare any variables we need so that we can write a Boolean expression. Examples using the relational operators. 1. Double check amount balance. If amount, a Boolean expression. If amount of the check is less than the balance, subtract the amount from the balance. Boolean expression. If check answer less than balance, subtract the amount from the balance. 2. String entered, password, real password. Boolean expression. If data entered at the keyboard is the same as the actual password, provide access to the account. Boolean expression. If entered password equals real password, provide access to the account. 3. CHAR my CHAR. I'm going to assume that's character. Boolean expression. If the first letter of the name is an L, increase the number of these names. Boolean expression. If my character equals L, increase the number of these names. 4. Int age. Boolean expression. If your age is greater than 16, apply for your driver's license. If age is greater than 16, Boolean expression. Apply for your driver's license. The compiler, through the if statements, makes a decision based on the value obtained from the Boolean expression. A value of true allows the compiler to execute the conclusion of the if statement. A value of false allows the compiler to skip the conclusion to go directly to the next statement. The important fact to remember is that the line immediately following the if statement will be executed no matter what. The only alteration for the compiler is whether it skips over the conclusion after the hypothesis. What the if statement allows you to do in terms of the decision model we discussed earlier is to put one outcome as the conclusion of the if statement. See figure 6.8. Note, the if statement needs a Boolean expression to work properly. Figure 6.8. A model of the if statement with one outcome. looking at the model. Boolean expression value, true, outcome conclusion, go to the next line. Boolean expression value, false, do nothing, go to the next line. If there is more than one outcome from a decision, you need to use another control statement. There is no place for a second outcome to be executed when using the if statement. The only second outcome that works in the if statement is to do nothing. A block of code. At this point, we need to introduce how to create a block of code, a group of programming statements that should be executed as a group. We use braces to block off a group of programming statements. The first time we saw these braces was when we introduced the main section of a program in Chapter 4. Braces are a way of instructing the computer that we are sectioning off some lines of code. With the control statement we just studied, the if statement, we needed to be able to write code for an outcome that has more than one instruction. Let's say you want to ask a person playing a video game whether she wishes to continue playing the game. If she says yes, you need to start the game again and reset the score. If answer is equal to yes, outcome, start game again and set score to 0. In another example, you will access your bank account only if your password is correct. If it is correct, you'll be granted access and asked what you would like to do next. Make a deposit, get cash, and so on. If password entered at keyboard equals password obtained from the magnetic strip. Outcome. Provide access, ask what user wishes to do, and get input from her. Note: whenever more than one statement is used in the context of a control statement, use the braces to make a block of code. The if-else statement. The two-outcome decision. The if-else statement is another example of a control statement. Like the if statement, it uses a Boolean expression followed by two conclusions, two outcomes. These two conclusions are executed according to the value of the Boolean expression. Let's first look at some examples of the if-else statement in everyday life. Examples: if Tom has to work tomorrow, I'll see him tonight. Otherwise, I'll see him tomorrow. If the repairs cost more than $2,000, I'll buy a new car. Otherwise, I'll get it repaired. Each example, upon analysis, has a Boolean condition and two outcomes. Let's identify the decision and outcomes for each example. 1. Decision. Option 1. Tom works tomorrow. Outcome 1 goes to see him tonight. Option 2. Tom doesn't work tomorrow. Outcome 2. See him tomorrow. 2. Decision. Option 1. Repairs cost greater than $2,000. Outcome 1. Buy a new car. Option 2. Repairs cost less than or equal to $2,000. Outcome 2. Repair the car. Now let's take each example and fit it into the if-else statement structure. Depending on the value of the Boolean condition, one of the two outcomes will be executed. If Tom has to work tomorrow, I'll see him tonight, else I will see him tomorrow. If the repair costs more than $2,000, I'll buy a new car, else I'll get it repaired. Each has the structure Boolean expression, outcome 1, outcome 2. Let's look at the table. Boolean expression, value, which outcome is executed. Boolean expression, Tom works tomorrow. Value, true, which outcome is executed. Outcome 1, I'll see him tonight. Tom works tomorrow. False. Outcome 2, I'll see him tomorrow. The repairs cost more than $2,000. True. Outcome 1, I'll buy him a new car. The repairs cost more than $2,000. False. Outcome 2, I'll get it repaired. The value of the Boolean expression determines whether outcome 1 or outcome 2 is executed. Whenever the Boolean expression is true, outcome 1, always placed first, is executed. When the expression is false, outcome 2, placed after the word else, is executed. If the hypothesis Boolean expression is true, execute outcome 1, else execute outcome 2. If the outcomes have multiple programming statements, then you need to use the braces around each block of instructions. If expression, Boolean expression, is true, execute outcome 1, first statement, second statement, third statement, etc. Else execute outcome 2, first statement, second statement, third statement, etc. Some examples in code. To save time, often we will examine only portions of a program. These are called program fragments. Rather than show the compiler directives and the main section for every example, we will just show a portion of the program that we need to study. Here is a fragment from the programming language C++. An example of the if statement is written this way. If x is greater than 12, see out the variable is greater than 12, and L. Note that parentheses are used to surround the Boolean expression in the language. Consider the following examples. Examples. 1. If a number is greater than 0, then inform the user the number is positive, else inform the user that the number is not positive. If the number is greater than 0, see out is the number is positive and L. Else see out the number is not positive and L. 2. If your age is greater than or equal to 16, then inform the user she is old enough to drive, else inform the user that she is not. If age is greater than or equal to 16, see out you are old enough to drive, and L. Else see out you are not old enough to drive, and L. Using a Boolean condition to determine whether a number is even or odd. In examples 1 and 2 that follow, we will let the computer evaluate whether a number is even or odd. In order to do this, we need to use the mod operator, gives a remainder in division, from chapter 3. Let's first review a few examples with the mod operator. 18, mod operator, 2 produces 0 since 18 is divided by 2 and 9 is with no 0 remainder. 15, mod 2 produces 1 since 15 divided by 2 is 7, with a remainder of 1. As you recall, The mod operator allows you to look at only the remainder from a division problem. 18 is an even number. All even numbers will have no remainder when they are divided by 2. So we write a Boolean expression using the equal relational operator. If a number is even, dividing the number by 2 gives us 0. If a number is odd, dividing the number by 2 gives us 1. Consider these examples using the variable x that has been assigned a value. Int x is equal to 24. X mod 2 is equal to 0. Is 24 mod 2 0? 24 mod 2, 0 equals 0, true. Therefore, x is an even number. Int x is equal to 17. X mod 2 is equal to 0. Is 17 mod 2 equal to 0? 17 mod 2, 1 is equal to 0, which is false. Therefore, x is not even, so it must be odd. Note, if the number mod 2 is equal to 0, then the number is even. If the number mod 2 is equal to 1, then the number is odd. So now we are ready to use the mod operator in the context of an if statement. Both fragments accomplish the same thing. One uses a Boolean variable, a holder for the Boolean value, and the other does not. Example: if a number is even, print a message saying it is even. Program fragment with a Boolean value. Int number cin is greater than cin number. Let the user give us the number. If number mod 2 is equal to 0, see out the number is even, and out. Program fragment using a Boolean type variable. Int number, Boolean answer. Both variables are declared. Cin number. Let the user give us the number. Answer equals number mod 2 is equal to 0. Answer holds true or false. If answer, see out, the number is even, and out. Notice that the last statement uses a Boolean variable in place of a Boolean expression. This is possible because the value inside the variable, answer, will determine whether the conclusion is executed. Example 2. If a number is even, print a message saying it is even. Otherwise, print a message saying it is odd. Program fragment with a Boolean value. Int number, cin number. Let the user give us the number. If x mod 2 is equal to 0, see out the number is even, and out. Else, see out the number is odd, and out. Program fragment using a Boolean type variable. Int number, Boolean answer. Both variables are declared. Cin number. Let the user give us the number. Answer equals number mod 2 is equal to 0. Answer holds true or false. If answer, see out, the number is even, and out. Else, see out, the number is odd, and out. The switch case statement. Decisions are generally made between two options. If you want to decide among more than two options, you can use a switch statement, as it is called in C++. Otherwise, other languages use a different name. Once you understand what this statement does, you will be able to recognize it no matter what it is called in any programming language. A switch statement works in this way. Think of this analogy. You are standing in a huge room that has 3 doors in it. Each door has a number on it. If you open door number 1, outcome 1 is behind the door. If you open door number 2, outcome 2 is behind the door. The same thing is true for door number 3. Behind each door is a different set of instructions that makes up the outcome. The switch statement evaluates an integer variable. That is, it looks at its value. Then it examines a list looking for that value. When it finds the value in the list, it executes all the instructions that are associated with that value. This type of control statement always has 2 elements. One element is where an integer variable is examined to see what value is inside it. Then the value is found among a list of integer values, and the statements, the outcome, next to that value are executed. Here is a diagram using our door analogy. Switch, door number 1, the statement number 1, statement number 2, statement number 3. Switch door number 2, door number, statement 1. Switch door number 3, door number, statement 1, statement 2. The actual switch statement would need to know that the variable used to control it is an integer. So we first declare an integer. Also, it uses the word case of instead of door number to list the integers. Let's do an example from a program that could be used at an ATM machine. The user will be asked whether she wishes to make a deposit, get cash, or check the balance of an account. If she inputs a 1, then she will expect to make a deposit. If she inputs a 2, she will be able to get cash, and if she inputs 3, she will be able to examine the balance of one of her accounts. In the program fragment that follows, the numbered statements represent undisclosed programming statement. INT, your choice, see out. Please choose your option by typing the number 1, 2, or 3 and out. See in, your choice. Switch, your choice. Open case 1. Statement 1, statement 2, statement 3. Case 2, statement 1, case 3, statement 1, statement 2. Close. Not all outcomes for an integer have the same number of statements. One outcome might be just one statement. Another outcome might have 3 statements. The switch statement is a clean way of choosing among more than 2 things. As you learn more about decisions, you will see that they can be more involved than the models we examined here. There are interesting ways to handle more complicated decisions. It just takes some practice to use the statements we have already mentioned in the correct way. The if statement with the if-else statement and some variations on those 2 statements, including using them together or one or both of them repeatedly, will allow any programmer to handle very complicated decisions of more than 2 choices and 2 outcomes. Summary. The Boolean type is another type of variable in addition to those we have already studied, the integer, character, string, and real. It is used to store the result of evaluating a Boolean expression. It always holds the value true or the value false. We examined how a decision can be modeled on options and outcomes. If you choose one option, it leads to one outcome. If you choose another option, it leads to another outcome. Control statements are programming statements that allow the compiler to alter the usual order of execution of statements. In our case, we want to skip over one line of code to get to another. One example of a control statement, the if statement, has two parts: a hypothesis or Boolean condition, followed by conclusion. It is used, ideally, for a decision that has only one outcome. The if-else statement has three parts: a hypothesis containing a Boolean expression, followed by two outcomes, only one of which will be executed depending on the value of the Boolean condition. If the Boolean expression is true, the first outcome is executed. If the Boolean expression is false, the second outcome is executed. The if statement can be used to determine whether a number is even or odd. This useful algorithm is done through the mod division operator. Finally, switch statements. A switch statement is a statement that is best applied to decisions that involve more than two choices.